About 40 years ago, my mother's family used their savings to buy 200 acres of forest in rural northwestern Rhode Island. My grandfather loved the outdoors and had a dream of building and running a campground as his retirement project. The focal point of the campground is 350-acre Bowdish Lake. When the campground was first built, with my grandparents and my mother and uncles doing most of the work themselves, the lake was a beautiful, pristine body of water which offered campers swimming, fishing, boating, and gorgeous views. My grandfather has since died, but my grandmother, who is 85, still runs the campground, which is her only source of income. About 10 years ago, a new water plant began to appear in the lake, introduced from the propellers of boats brought to Bowdish from other affected lakes. This was the start of an invasion by the non-native Eurasian water milfoil, or Microphyllum spicatum. Eurasian water milfoil is actually a close relative of eastern water milfoil, which is native to the New England area. However, the Eurasian variety produces approximately 2 to 3 times as many leaflets, or 14 to 30 feathery leaflets along its thick 3 to 12-foot stem, and is capable, under optimum conditions, of growing an inch per day. In addition, it spreads by fragmentation, so boat traffic can cause the weed to occupy an entire body of water in as little as 2 to 3 months. Currently, the weed has overtaken every part of Bowdish Lake, making swimming an experience from a horror movie, as thick ropey strands of water milfoil coil around your arms and legs, dragging you down under the water. Boating is tedious as you have to stop frequently, lift the engine and cut the weeds from the propeller blades and shaft. The water milfoil forms a dense mat of vegetation that blocks the sunlight from native plant species. The decay of all this organic material leads to excessive phosphorus and nitrogen in the water. While the lake used to offer excellent fishing for largemouth bass, fish seem practically non-existent as the excessive plant growth has adversely affected water quality. The heavy biomass leads to low oxygen levels under the matted vegetation, increased pH, and increased temperature, all of which adversely affect fish. Even the beautiful view is ruined, as in June the plant sends thousands of shoots above the surface in a creepy display of dominance. Last summer my grandmother, knowing I was interested in science and engineering, asked if I could do some research and come up with a possible solution to the problem. I found that current control methods are either very environmentally damaging or expensive. The best options I could find were mechanized harvesting and the milfoil weevil. While the weevil is theoretically capable of eradicating the weed, giving a density of 3 weevils per weed stem, which no other control method could achieve, they proved exceptionally hard to source, so harvesting became the top option. However, due to the nature of the machines available, mechanized harvesting is both inflexible and expensive. The solution, then, seemed to be to reshape the mechanized harvesters into a more flexible platform, and this idea was the genesis of the EW, or Experimental Underwater Weed Whacker. The overall dimensions of EW's frame are roughly 2 foot by 2 foot by 2 foot. The frame is constructed out of 1.5-inch Schedule 40 PVC pipe and fittings, with the exception of the center compartment housing, which is 3-inch Schedule 40 PVC. Junctions are entirely PVC cement, largely resealed with silicone and tape to ensure waterproofing. All wire holes are silicone sealed. The camera lens cap is a modified PVC drainage fitting with a Lexan lens. Propulsion is provided by forged bilge pump cartridges, 2 for vertical thrust and 2 for horizontal propulsion. The 2 providing propulsion horizontally are rotated by a waterproof high-torque servo motor for steering. Another 2 cartridges are responsible for rotating the saw blades. All power is provided by a trio of 6-volt 3300 mAh rechargeable batteries. Control comes from a trio of electronic speed controls, which are connected along with the servo motor to a Spectrum radio control system with beyond line-of-sight transmittance and range exceeding 1 mile. The speed controls and wiring are contained within the central 3-inch PVC pipe. The 2 halves of the robot come apart to allow for access, and vision comes from a camera mounted in the front of the robot behind the Lexan lens mentioned earlier. The cutting is provided by a pair of 7¼ inch finished circular saw blades. Originally, I planned to use a pair of bilge pump cartridges for directional steering. However, as that was very expensive, I changed my plan in favor of using a servo for steering. Figuring out the servo proved difficult, however I eventually figured out a solution using some spare servo arms and electrical wire. I also thought I would be able to find the propellers I needed at a hobby shop. This proved impossible, as I could not for the life of me find a propeller anywhere that would fit the shaft of the bilge pump cartridges. Luckily, the UPS store at American University, which is in my neighborhood, is one of the few in the country to have a Stratasys Uprint SE Plus printer. Last summer, during my internship at the U.S. Naval War College in Newport, Rhode Island, I learned how to use Autodesk's AutoCAD software. Using AutoCAD, I found available for free students on the internet, I designed the propeller parts I needed and had them printed with a 3D printer at UPS. I was also able to print the brackets I needed to attach the saw blades to the bilge motors. The prototype U was finally ready for testing in October. I drove the robot up to Bowdish Lake during a college tour for its first test. On the first venture, the robot, which weighed more than 15 pounds, rode only about halfway down into the water and would not operate effectively, since it was full of air. I rapidly added some ballast, but the robot experienced severe ballast imbalance and still would not operate correctly. The next day, I used pipe clamps to rearrange the ballast, and the robot was finally sitting level in the water. However, by the time I finished correctly adjusting the ballast, the servo responsible for the steering had become inoperative, possibly because the wiring became disconnected, and I managed to lose one of the saw blades in the lake. So the test that day, my last day there, consisted of solely a cutting test, which went smoothly. Despite some minor clogging issues, the saw went through the weed with ease. The robot also experienced some leaking, but luckily the water inside the PVC pipes was not sufficient to affect the electronics. Back in Washington, I made modifications, including resealing all the joints with more silicone followed by duct tape. I also reworked the AutoCAD design to make the propellers larger and had those printed. Further testing, purely for mobility, was carried out in nearby Rock Creek. The saw blades rotate in opposite directions, as not to affect the steering, so since the ballast was adjusted for a single saw blade at the time, I only put one on, and spinning it caused the robot to veer. Otherwise, the robot functioned exactly as planned, with all systems functioning simultaneously and as intended. After a final visit to the 3D printer for a replacement saw blade bracket, the prototype U is now ready to do battle with Eurasian water milfoil, hopefully working in tandem with some milfoil weevils, at Bowdish Lake this spring.